Okay, hi everybody, let's get started. Hope everybody's doing pretty good today. I'm gonna lower the music a bit. Okay. Alright, so today we're gonna start on like the beginning of the modding process for the game. And probably one of the simpler aspects of it for our purposes will be the actual movement calculation for the pieces. So I guess let's just get right to it. Oh well, first I should probably acknowledge that if you were here for one of the first streams, we're obviously at a different time now. It's mostly because I wanted to try to stream every weekday, and I wasn't able to at the previous time, so I hope this time is okay for everybody. Also, some days I think we'll be actually playing some games for, well, I like to call it research, but it's just so we can see some of the other ways that other developers have made tactical games like we'll be doing in the future. So yeah, we'll see about that. Okay, so the main bulk of the move option calculator is obviously this function. And what pretty much anything in the program can call it, and it will pass us the behavior ID and the starting position of the piece, and then we'll need to return a list of possible positions that that piece can move to. So first let's just set up a dummy. So that it'll stop bothering us about an error. So there, now, if anything calls it, it should run, but obviously this is garbage data. Now, where the actual data for the piece movement is in this piece behavior class, which we set up a while ago. Right now it just has this integer move type. We're actually not going to use this because it's a little simplistic. I think, yeah, let's make another class that will just hold the piece movement, because it might have quite a bit of fields in it, and so we don't want to muddy it together with the rest of the piece behavior. Okay. Just our namespace to keep things clean. Okay, so the first thing, what I'm envisioning for how this data will be held is we'll have like an array, a 2D array of well, I'll just have it integers right now, but we'll probably change it to an enumeration. But the game will look at each entry into the array, and from there it can tell if the piece can move to that position relative to whatever position is passed. So for example, I'll just make a simple 3x3. Okay, so in this example, 0 means you cannot move to that position, and we'll use X to denote the actual piece. So this means the piece is in the middle. So for a checker piece, well, actually, I guess we'll just do a pawn, a simple pawn at this point. So this, a 1, we could use that to mean that it can move to that position, so the pawn can go 1 upwards. Obviously, if this is, we'll flip this for the other player. I think black is on top. I don't know. But for the second player, we would flip it so that they could only go forward from the place there, from their perspective. So we can also, just from looking at the pawn, we can see that there are multiple types of movement, because it can actually move 2 pieces ahead on its first movement. So we'll need to model that with maybe option 2, and then it can move diagonally if it's taking out a piece. So that's option 3, and so for that we actually need, that makes it obvious that we need to have an enumeration of different movement types if we actually want to make the pawn. Ironically, I think the pawn is probably the most complicated piece in chess, at least for our purposes. So let's see. The first thing should be impossible. And I guess we'll just have the self option, which would be the X. Open space, which would be the 1. Well, I guess it does. I forget. Can pawn? I don't think pawns can move forward and to take out a piece, actually. So yeah, I guess 1 would be only open, and then we'd have only enemy, and then 2 would be something like only first move. Then also we just need the simple option. I guess we can just say anything. And so with this we could model a pawn. But then of course let's take a rook for example. And so we have an 8x8 chessboard. I'll just set everything to 8. Or everything to 0. And so if the rook is right here, then we would model its movement as a 1. And so, but obviously the problem with this, well, there are 2 problems with this. Say this place here in game is actually filled with any piece. If it's a friendly piece, the rook couldn't move there or any place after it. But if it's an enemy piece, the rook can only move there and then no place after it. So we obviously need to have, what should we call this? I guess blocking. And then we can maybe even simplify it, because one other problem with this is that it assumes an 8x8 board, and it also doesn't define how the rook can move downwards or to the left. So I think an easier way to do the rook would be something like this. Where the asterisks would be, you could think of them as a repeating, so the rook can move infinitely to the left, right, up, or down as long as it does not run into any other piece. So we'll call this blocking, repeating. This should be open or enemy, actually. Well, somebody could want to mod a game where you can take out your own piece, so I'll leave the anything there. It won't it won't add much complexity. Okay, so the blocking repeating, we can also model the bishop like this. So that would be the bishop. And then the queen, we could model like this as well. Now, one other piece which is kind of strange is the knight. I think it has 5x5. So this is the knight could move basically as this kind of pattern. But the problem, well, actually the knight, we can already do the knight. I was going to say the problem with the knight is that it's not blocked, but it doesn't have the blocking pattern, but we can just use the open or enemy flag for all those pieces and it actually would work perfectly. Now let's say this is like a hypothetical piece that we could also model. Let's say we have something like this. What would that mean? It basically mean the piece could move. It can't hit this first, but then it can move anything to the right, which I think that makes sense. But what if we wanted to do something like this? Maybe we're getting a little too complicated, but it's kind of fun to think about what you could do with all these tags. I think that the engine would probably just say this is an illegal configuration because it doesn't make much sense, but I guess you could kind of think of it as skipping, being able to skip every other space. That could be kind of fun. What would we call it though? Maybe pattern. But we can do more things as they come. One reason I thought about this is because I was trying to think how would we model checkers. Because checker pieces can jump over. They can either move, if I remember correctly, they can move one space in any direction or they hop over infinite pieces. That's a bit... I'm not sure how we would do that in this, using this engine. I think we would almost need to have multiple options. So the checkers would have actually they can't move backwards until they turn into a king, or sideways, I think. Okay, good. I'm glad I remember, right? It's been a while since I played checkers. So this would be maybe table 1 for a checker piece, and then table 2. Basically, I think it actually need multiple tables because like for here, it can jump because it can only move to this position if there's an enemy here. So I think the checker, let's see, it needs like 9 tables total, because then it would have this one. And this one. And this doesn't even like account for double hops, so I think maybe for movement we'll need to have this option to repeating like a valid move takes into account where the piece lands, and then it does the calculation again. And if that's the case, we don't need this pattern, because it just, you can do the same thing with this repeating option. And to avoid confusion, I'll call this blocking infinite, I guess. I will look, I think instead of making this a 3D array, which seems a bit much, we'll just maybe move some of this out here. Oop, I took away the wrong thing. Trying to think of the best way to store this. I wasn't thinking about the having to have multiple options. Well, I don't really like having a 3D array, but I think it is probably the best for now. Now for the case, you might be thinking that checkers also change and that they can move anywhere once they become a king, but we'll model that some other way. Like we'll actually have the piece transform into a different piece. So that's it'll just have a whole separate movement data. Okay, so now that we have that, did we actually make a way for classes to access this? Oh, okay, we did in the game database. Which is not populated at the moment. Okay, we'll probably change this, but for now, we'll have the chess scene just create a new game database object. But we'll probably change this because the game database can be loaded once and then just passed to the chess scene in the future, probably. Although, of course, mods do complicate things because the player could turn on and off mods between matches. Actually, does not really need to do that. We'll just have the we'll just add this to the components since we're going to change it in the future. I'm not going to worry about what happens when the scene's deleted, so we won't do a janitor and all that for now. But we do need to do a key. I can't spell. And then from there, the move option calculator will have a reference to the game database. Which it will grab from here. And okay. Alright, so first we need to get the piece behavior object. You can do like this. And since we know we have this repeating thing, which we will use, like I said, for checker pieces, this function, or this calculate move option, should probably be recursive. which means that it should be able to call itself with new data. So let's go ahead and do that. So we'll pass it the list. Pass it the piece behavior. And for now, since we're using a 3D array, I'll pass it the table index, I guess we'll call it. And then starting position. For now, well, we can go ahead and assume, let's go ahead and do the easy option, which is a non-repeating movement. Oh, I also forgot. I made these public. I guess there's nothing really wrong with a 3D array. I'm just used to, in Unity, it doesn't know how to display more than 1D arrays in the debugging screen. So I try to keep things 1D. But I'm not sure there's a really easy way to do that here. I guess you can always flatten it because, well, no, we shouldn't assume that each inch or each table is the same size. Because for instance, this first checker one could actually be 3 by 3. Maybe the best way to do it would just be to make an internal class. And then all we have to do is here, we just have an array of tables. That's a bit cleaner, I think. I wanted to go ahead and finalize that because we don't want to do a whole bunch of work on here and then change the data structure. So if the move type is not repeating, then we just calculate from the table. Since we have, we can just change this to so it'd be behavior, move type, table 0. We'll just assume only 1D, like there's only one table for now. And then starting position. Okay, so now let's see. How will we do this? Most of these are really simple because they don't actually care much about the context of what's going on around the piece. They only care about the tile itself. The only one that is more specific would be this blocking infinite. But I think that we first should cycle through the table and find the offset where the piece is supposed to be. Or going back to our test tables here, we need to find the position of the X. Be length. And since table is just a data class, I'm just gonna treat it as a structure and just access the fields directly, as they're public fields and not private. So if the option here is self, then we know we found it. Okay, and the way that we turn this index into the actual 2D position is that's the reason why I have the columns in here. So if you've never seen this operator, it's called modulo, and it's just a fancy word for taking the remainder. So say if we have a 3x3 table, then we have 3 columns. If this I was 4, then it would or if this I was 3, then we'd be talking about this space, and so 3 divided by 3 has 0 remainder, so it would give us this column. And then division with 2 integers always rounds down, so 3 divided by 3 gives us 1, and so we'd get 0, 1. And then you can go through and determine that you'd get all the right piece for each index, or the right position for each index. Maybe we should, I'm not sure if we should do let's assume that the piece movement data has already been validated by whatever imported the mods. So, because obviously the movement table would be corrupted if it had 2 of these self values in it. But we'll write another piece of code that will make sure that the movement data is good, because this calculation shouldn't really have to worry about that at this point. So now let's think of some examples here. what would we do? Okay, so I'm gonna say that if something like whenever we see the blocking infinite, it looks at the direction it is from the X and then we'll continue it infinitely. So if you do something like this, that means that you can't move to this position, but you could move one over. And then I'm gonna say that doing something like this is probably invalid because it's not an even direction. So we'll say the blocking infinite can only be maybe to make this simpler, actually, now that I'm thinking about it. We should probably maybe force blocking infinite symbols to always be right next to the piece. I'm not sure about that, but that would be a lot easier to calculate, but it does kind of constrict some of the mod's options. Another option we have is just to not even have this blocking infinite thing. And well, I think we still need the blocking option, this blocking, like the blocking behavior, but not the infinite part, because the modders who create the pieces maybe would already know the size of the board. I'm not sure what would be easier. Or, actually an even easier way to do it is we don't need the infinite, because now that we have this repeating thing, once the piece, we could just do something like this. Oh no, that wouldn't work actually. Because if we had something like this and we turned repeating on, I'm trying to think of a good way to illustrate this, but I'll just make an 8x8 board real quick. Okay, so if we had this rule with repeating on, then the player could do something like this, where they'd start here, and then they'd move one to the left, and then they could move one down. Like in our system, it would let you do zigzags, it wouldn't actually care about the previous turns. So I think we do need this infinite rule. Never thought chess movement would be so complicated. Well, let's just start with the simple ones that we know we'll use. We'll think about how to do this blocking one in a second. So for these, they only care about the piece or the spot in question. They don't care about the context of the rest of the board, or even where the player is really. They only care about the spot and what's on it. So we'll use a switch statement here because it makes it easy to go through all of the enumeration types. Okay, so since this is an anything, all we have to do that's all. We don't have to do any validation or anything. Okay, so only now this is something we haven't got to yet. How does it know? It doesn't know the state of the board at all. So we have two options here in order to find if a space on the board is clear or not. The first thing something could do is loop through all of the pieces and just check the position to see if any piece is on that space. The second option is if the board object tried to keep a 2D array of what piece is on what position. Obviously that is a lot faster, but you open yourself up to bugs because you don't know for sure. Like, the board would have to keep track of every change. And the maximum length of this piece, or this list, well, for a normal chessboard is 8 by 8, which is 64. So you couldn't have any more than 64 pieces, but I guess people can make arbitrarily large boards. But I think we'll just go the simple way, because just to reduce bugs. And then for some reason, if we see we have performance issues, we can do something more complicated. Let's have the board have a helper function. What is it complaining about? Oh. Now it'll return a -1, we'll say, if there's no piece on that spot. Actually, we can't use a for each because we need to know the piece index, so. Okay. So if it finds any piece in that space, it can just go ahead and return its index. Otherwise, we'd return a -1 if the whole loop finishes. I don't think we need to make a remote function like we were going to do for this calculate move options, because objects are already going to have a reference to this board object. So the next step, obviously here all we just need to see oh, did I make it private? I probably did. Yep. Okay, we need to change this, but so we do something like this, but this starting position isn't going to work. So we'll do the same thing we did over here, except for this new index. Yeah, I actually did that wrong. It should be the space offset. Well, let's see here. Because all these are relative to the actual piece, so it should be yes, that should work. Okay. So see what we did here is back on this option. Our starting pose that we're past, let's say the game wants to find out the movement options for a piece on 3-5. Then the piece offset, which we're looking at this table, is 1-1. And then the space offset, let's say we want to find, say this piece can move forward, so we want to find this. And the space offset would be 1-0. Actually, the space offset, well, this value is 1-0. So space offset is 1-0 minus 1-1, so we'd get 0, -1. Because space offset is relative to the piece offset. Hopefully that makes sense. Feel free to stop me. Similarly for the only enemy, we do something like this, but we also need to know what player is wanting the move calculated, so we need to actually pass a third option here. I could just pass the piece object instead of all these values, but I mean, it's conceivable that you'd want to ask this calculate move options for a piece at a different position than it's at currently. Maybe a better option would be to do something like this. And then we'll change this to using position. So it won't actually use the piece's current position, it'll use whatever we pass right here. So we need to change this remote function to ask for a piece instead of a integer. And so now that we have that, okay, to clean things up, you can add these little brackets. And if I didn't add them, then any variables I declare under this case would also go down in other like so if I did something like this without those brackets around it, then it wouldn't let me declare another one here because this variable would still be in scope. So if you add brackets, then you can call both. Right now it's saying that this value is not used, but we knew that. So what we want to do find the piece on the space, and then if there is some piece there and the owner player does not equal. Okay, see, we need to move something else here. Does not equal the moving pieces player. Then we know we can move there. Okay, so then the open or enemy this is all you have to do is just change this. So you can move there if there's no piece on the space or the piece is a different player's. The next thing would be the only first move, which we need to simulate pawns, since they can move 2 spaces forward on their first move. The question is, though, do we want to abstract this further and make some... We could make some option that certain tables could be called on different turns. I'm not sure if we do. I think we'll just stick with this simple solution first, where we only support move on the first turn, or different moves on the first turn, I mean. We can always change the behavior if we need to in the future. So this means that the move option calculator actually needs to know what the current turn is. But I don't think I really want it to have access to this function or this class. But things will need to know what the turn is, so we should probably just have, we can use this simple, what do I call it? Simple int subscribable, which just sends out a function whenever, or sends out an event whenever this integer changes. So we can use it pretty simply to have it track turns. Oh, where'd it go? Oh, it's over here. So we'll go ahead and do a janitor because it's pretty. Oh, it does need to have a reference to this. And we'll make another entry to the component keys. We'll call this current turn. Go. Let's make this easier. This is even better. And I'll just have it take an initial value in the constructor. Oh, I spelled it wrong. Alright, so all this does is now we'll have an event when the turn changes. So the move option calculator doesn't need to hold this anymore. Then we'll just add another listener. Oh, we don't want a component. I always forget what you put in the type. Okay. So all I'm doing here is giving, or trying to find the current turn event. We'll give it the key, component keys. Then we just need the new listener. We can actually just do an anonymous function because all it needs to do is cache the value for when we need it, because we don't actually have to do anything. Okay, what's wrong here? Oh, I see. There we go, that's better. Okay, so now we have the current turn. Except, I just realized you can, this isn't only the first turn, it's the first move, so we actually don't need this. Well, we're gonna need that event for later, so it's no big deal, but that makes it obvious that we need to have some other piece of data in the piece object. Let's say number of moves. So then we check this number of moves for 0. So yeah, I was making much more complicated than it needed to be, but also looking here, I just noticed that we have this is captured flag that I forgot to take into account. So here we need to make sure that the piece also isn't captured, because if it's captured, it's not really on the board. So that's all we have to do for that. Now for the only first move, well, for pawns, how it works, I think, is you can't capture the piece using this. So we'd want to have it only open. So I'll just change this to only first move. And open. But we're starting to see that there's really a few different options. Because for example, we care about like what's in that specific spot. We care about the number of turns. And then we care about if this cares about the previous movement. So there may be a better way to model all of these options. So let's just do an experiment here. Let's say that we actually, this table had an array of these option classes. And then we have this other enumeration for and then we actually want this to be flags, or another word is a bit field, where you can have any combination of these flags. In order to do that, it's really easy. You just have to put this tag before the enumeration and then make sure each entry has a power of 2. So we'd have like field requirements, before movement requirements. And then I'm still not sure the best way to handle this, because it's kind of different than everything else, because it cares about how we moved before. We'll come back to that. I think we'll go ahead and convert to this, because it makes, even though it changes these options from being a simple enumeration into a whole nother class, it kind of will simplify the logic a bit, I think. Okay, so now we have lots of errors here because we're not using the enumeration anymore. So now all we have to do, instead of checking what kind of enumeration it is, we just look at the other objects, or values in the field. So first we'll get the piece on the space. If nothing else, we'll assume it's possible. So let's go ahead and get the option object. Okay, So if the option, okay, this means basically that the option wants it to be filled, or wants it to be an open space. Actually, this should start false, so I got it backwards. So this means that if the movement option wants the space to be open and there's no piece on the space, then this is possible. Otherwise, if the option will also be fine with an enemy on the space, and as we checked before, then this is also possible. So if the option will be happy with an enemy on the space, there is a piece on the space, and the piece has a different player, then it's possible. And the last option is if there's an ally, and it's just the same except it has the same player. So if it is possible, then we can go check other things. And so we need to do the first move. Let's say if it is possible, and oop. So if it has a before moves requirement, I'm going to rename this. Then we'll also need to check that is possible. Would be the piece. Oop. Yeah. So we just need to make sure that the number of moves is less than the before moves requirement. And at the very end, if it is possible, then we just add it to the possibility list. Oop. There we go. So now we have a lot more power here, because we can mix and match any combination of these requirements. So now we're back to the pesky blocking rook movement. I think it would be really nice if I could somehow get this repeating option to work with it. Maybe we can have different repetition options. So let's see. didn't spell that right, I don't think. But so none is just default. Then any table would be like this checkers, or once you move here, then it checks all the tables again. Except that's not true either, because once it moves, once you jump over a piece, you can't do this type of movement again. So that shows us that we actually need to have this repetition mode inside the table. So basically, if we have repetition on, then you can repeat into the table indexes that we'll define here. So for this, these can repeat, but they would exclude table number 1 from their list. And then this table would just have an empty repetition array because it does not repeat. And then just for ease, we'll keep this function here, or this value here. So then how would we do the chess piece? So let's say this one is open or enemy. No, actually, how we would do it. So you'd have this table 0. And that 1 would be only open. And then table 1 would be like this, and the 2 is only enemy. The difference this would have an empty repetition array. So basically, once this table is used, then the repetition would stop. So I think this is pretty powerful. I mean, it's a lot more complicated than the original version we had, but it lets us do all different kinds of pieces. So, and it actually is a lot easier to define than having the old blocking mechanic that we are going to use for the rook and bishop. So let's go ahead and just make a rook. So we already have table 0 and 1. Two, three, 4, 5, 6, 7. And then this. Then we'd have this, and it would repeat with 2 and 3. And we'd have this, and it would repeat with 4 and 5. lastly, this would repeat with 6 and 7. Okay, I hope that makes sense. We're basically going deep into recursion, but I think it's the best option. And then I also realized a problem that we have with the checker is that this E, the X cannot actually land there, but it just needs to make sure that there is an enemy in that position. So we need to add something like this. And that shows me that we actually need to loop through the entire table to make sure that everything is valid before we add anything to the possibility list. So let's go ahead and do that. So actually what we should do for simplicity, we'll go ahead, make another list. We'll just call it maybe possible. And we'll add things to this maybe possible list. And then if the that's what the option is, a move to option. And then we'll need to move this is possible value outside of the loop. Let's change this to I think, yeah, okay, let's change this to is option possible. And then we'll make an is table possible. And thinking about this, I think we should move the before movements outside of the option and into the table. So we check the movement thing here. And then just as if table if it has a movement requirement and the piece number of moves is what's going on? Oh, the option is not defined. Okay. Oh, of course. and then the number of moves is, let's say that's greater or equal, then we'll actually just return because we can't use this table. And then if we find out that the table is possible, then we'd add all the maybe possibles to the possible list. So there we go. And then what makes the table possible is basically possible if all of the options are possible. We should change this. Was it not like that? Oh, I see. So if any of these options are not satisfied, then we'd break the loop and the table is not possible anymore. So this is a little cleaner. Okay. Alright, I think now we basically got it all done. So now we just need to worry about these repetition. I just realized that as we call this multiple times, the possibility list might actually be like filled with duplicates. So instead of a list, we'll use something called a hash set. And the nice thing about that is that it can't ever contain duplicates. If you try to add another thing, it won't add it, and it's automatic. So it's slightly slower than a list, but as I said before, we're not really going for we're not going for speed right now. Oops. Okay, so now it's not complaining about anything. Maybe before we go any farther, it's probably a good idea to test this. Where's the board creator? Okay, so this makes boards. We need something to make just some test. I think I'll just have the game database build it. In the future, we'd want this to actually load the data from Unity. Actually from the mods through Unity. But we won't do that for now. Oops. Okay, so we need... Oh, where'd it go? So we're just creating test behavior here. So let's make a 3x3 table. We'll just do something really easy. Oh. It's going to be quite ugly, but it's just for testing. So we have 3 columns. Oh. I always do that. It doesn't like semicolons in here. No repetition. Then we have no before moves. So we'll have 9 options in here. Let's just check a simple piece that can move left, right, up, or down. So this position is 0, 0, so it's diagonal to the upper left. So it would be you can't move here. Actually, I don't have to do anything except say how would we do it? Basically, okay, so if I set field requirements for 0, then I think what would happen here is option satisfied would always be false, because basically, I guess to make it simple, I could just say that if the field requirements is 0, then option satisfied is automatically true. Another way to do it is just to say field requirements is anything. Which you can do like this. Oh. So this means the field requirement is open or enemy or ally. And then move to false. So this is like directly in front. The field requirements needs to be open. Yeah, let's just do open now. Then this is another diagonal piece. To the left. Okay, this next one is actually, yeah, the self object, so. Oh, of course, no semicolons. To the right. And the bottom row is the same as the top row. Is that 9? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let's go ahead and make both of these behaviors 0, since we actually care about what's in that value now. And then finally, we need some object that will basically just call the move option calculator and print out the possibilities for us. So I think to do that, I'll make another object. Okay. They'll need to be passed. Game object, because it needs to get components. So then what we do, we'll need to get the remote function. I can't spell. Okay, so that's the return value, and then we pass it a piece, and then of course this position we want to use. What do we call it? Oh, move option list. Should probably call this move option list query or something. Okay, so we need to actually get the piece objects, of course. Game board. So we'll go ahead and send this query just for the first piece. And let's set it in the middle of the... That's actually something we haven't taken into account yet, the boundaries of the board. That is pretty important actually, but... Okay, so... Oh, you know what? I'll make it a little more. A little cleaner. And so then we have the list. Okay, and so now we just want to print every object in the list. Simple. So now we go to the chess scene, and after everything, we'll just instantiate this piece move tester. Of course, this will be removed later. Okay, so let's see what happens. Okay, nice. Okay, so this remote function had not been instantiated yet. I think, yeah, it's because I hadn't actually done the instantiated the move option calculator. Okay, it's still not happy about something. Maybe we forgot. No, it's right here. Okay. It's always a good way to see if something is null or not, or what is null. Okay, so the remote function is not the null part. Is the board null? Oh yes, of course it is, because it hasn't been created yet. What does it not like about that? Oh, it's missing a bracket. Because this whole thing is a type, actually. Okay, so we need to call this do test function when the board is created. So doesn't it? I think it sends a message out. Yeah, the board created message. I'm not gonna bother with the janitor right now because we don't really care. This is just a tester, so. right? Oh, of course we don't have. We do need to cache the game. Okay. This still doesn't like something. The board's still null? Maybe the piece list is null. I don't think so. Yeah. Oh. That was a problem. I didn't set the query to be the instance object. Okay, so now we actually called the function and we're getting other problems. And again, we called the board before it was created, or we cached the board. So let's do the same thing. No, I will do a janitor here because this is an actual object and not just a test thing. Okay, so what we want to subscribe to again is the board created message. Okay, and so all I want to do here is cache the board. Okay. So all this does is when we get this message, which is the board created message, is going to call this and cache the board value for us. Okay, so everything ran correctly, but we didn't get any valid movement. Yeah. Well, that's a little funny, isn't it? I guess not. There's plenty of possibility for bugs in here, that's for sure. Let's do some debugging here. Okay, so we're just going to pass a whole bunch of values. the index, space offset, the actual place on the board, if it's satisfied, and then I'll go ahead and pass the filled requirements just to see. Okay, so option 0. Oh, I see. Okay, that actually exposed an important bug. Obviously, let's go back to the database. So it messed up here when we said is self to true because it's still looking at the filled requirements. And as I was talking before, the filled requirements here are 0. And basically that means that nothing would ever satisfy it. So we need, basically if the option is the self, then we just ignore everything. So let's try it again. Oh, I did it backwards. So now it's only checking the self, so I need to do it the other way. Okay, so now it actually is returning. Now we can move to 5-5, which is down. Why is it only giving us that option? True. Yeah, because they're all. It should have should be 5-5, 3-3, 3-4, and 5-4, but. So let's see here. To make things easier, I really need the space offset. I'm just going to rename this to space and go ahead and just make it the actual place on the board. Let's rename this as a there to make it consistent. So now don't have this offset anymore. Why would it not be moved? Let's add another debug here just to see if this is getting called every time. Okay. So yeah, they are. Oh, there it goes. I don't know what was happening before, but we fixed it. So yeah, now it says possible movements are 4-3, 3, 4, 5, 4, and 4, 5. So let's make sure that's right. So 4, 3 is up. 3, 4 is left. 5, 4 is right. And 4, 5 is down. So okay, so we got a little bit left. Let's see. Let's go ahead. I guess we can start on the next part. So really, this doesn't matter anymore because we just try to make everything repeating based on the where is it? Right here. On the repeat with tables options. So we actually need another list here. This calculate from table should actually just return its a list of values that it found, because we'll need to call it again from for every movement it found if it's recursive. Oh, but I know something we should do first. We should check for the bounds of the board before we move it, before we add anything. So what we'll do here is the option is not the self piece, and let's make a helper function here, board in bounds. I'm gonna make this public. So what we'll do, this is true if the space dot x is greater or equal to 0, and space dot y is greater than or equal to 0. And then they both have to be less than their respective value in the dimensions. So now if space is in bounds, it'll loop through here. So now we have the possibility that everything is out of bounds, in which case the table is not possible, but this would still be true because it never reaches this place, or it never reaches right here where it's turned false. So what we should do, if maybe possible, then is table possible is false. Because there's no possibilities from this table, then by default it can't recurse into here. So there, we fixed that problem. Pretty simple. Now what do we want to do here? Okay, we can just use, like, this may be possible, it can just be a list because we iterate over each position once and only once, so there can never be copies in the list. So let's just have it so now we don't even need this maybe possible list actually. And then we'll change this so that if the table is not possible, we'll clear the possible list. Yeah, it could be, you could save a little bit if you did else if, but I think it's clearer if I leave it, so I'll leave that. So now this is just passed. And the reason I haven't it pass a list is because we don't want to have to create the list for every time this is called, because it could be called several times. And that's just an easy optimization that doesn't really cause any problems, so I'll just go ahead and do it. I'll say possible from table. We should actually do that after this behavior. But okay, so what we'll do we'll loop, we'll try each table. Let's go ahead and get the table. What is it? Piece movement data. Okay, so actually this should be, I guess the first time it does it this way, but I think we actually need another helper function. Because what we'll need to do, let's just do this simply first, because we don't have a whole lot of time left, so I kind of want to get a little bit over with. So we're going to do this with no recursion first. So if the calculate from table is possible, then we just add all the possibilities from the possible from tables list into the possible hash table. Too many too many possibility and possibles. Let's change the name. There we go. Now what we'd also do here is we would take each of these spaces and then call this calculate from table again. And then each of those would call calculate from table again. So we need to basically extract this. I don't like the order. So just rearrange things there to make it more standard. What does it not like? Oh. There we go. Okay, but the thing is, okay, so what we do here I'll go ahead and clear this. Is like for every space we need to call this function again on every table defined in the where is it? Repeat with tables. So you actually need to call one more. I think this should just clear it, just to be safe. Okay. I'll pull out this value here because we're going to need it. Okay, so we add it. We're actually going to need another list because this list is going to keep being cleared and we're going to need to keep track. So, you know what, I think just in the interest of making this simple for now, we'll just go ahead and have it return a list every time. This is like really very inefficient, but there's no easy way to do this. That's a shame. I guess we'll just do it this way. Alright, so now we call this recursive calculate from tables again. And we don't actually use this using pose, we use this space. And then we don't use this table again, we use every table and the maybe it does go like this actually. In the recursion list, oh, table index, okay. So for each okay, so this is the gist of it. This is very vulnerable to, well, anytime you do recursion, it's vulnerable to infinite loops. So before we go, I'm going to add a quick depth check. Basically what happens here is you, oh no, this is supposed to be 0. You add 1 to the current depth, and then here, if ever the depth matches the max depth that we defined up there, then you just return, because you don't want to have an infinite loop. And if that happens, then you probably made a mistake somewhere. Alright. Well, I guess we can, this should still work, so let's test it and see. I mean, theoretically it will. Oh, and it does. That's very nice. But of course, haven't tested this recursion yet. Okay. Just recap. So what happens here is that for every table, you call this recursive thing first, and then it checks if the table is possible. Then it adds every space that it returns, and then also for every table that we define in this repeat with tables value, we call the recursive calculate again. So then that just keeps going. And of course you need to be careful not to have loops. Now that I'm thinking about it, I mean, it does technically work, but it works great for chess, but with things like checkers, the path you take in each of these steps is kind of important, because things happen. So, we may need to actually change this again. Well, we can still use this for our rooks, but once again, checkers is turning out to be more complicated, because we'll need to, like I said, keep track of every step in the recursion. I'm not quite sure how we'll do that. We might not even support it really, because it is quite it's a lot different than everything else, so but I'll think about it. Alright, well I think this is probably a good place to stop actually. So I want to thank everybody for watching. I'll be back tomorrow, same time, 5 p.m. Eastern. And I'm trying to decide, we might actually be trying a game tomorrow, because I was thinking Tuesday, Thursdays would be quote research nights where we play a game to research about whatever we're making, but I kind of want to finish this this algorithm, and I'm not sure I'm not sure what game we'd play first anyway, so anyway, I'll keep you posted. No problem, Steph. Thanks for watching. But anyway, I hope you all have a good night, and I'll see you tomorrow. Right, bye-bye.